As we go into Chapter 4 now, we're going to take a look at exponential and logarithmic functions. And in Chapter 4, we cover the first three sections: exponential functions, applications of exponential functions, and logarithmic functions. We skip 4.4. In section 4.1, we take a look at exponential functions. And here you see a traditional function where x is the variable, in a sense, is a number, and the exponent is actually a number. Now, when we look at exponential functions, we have a number, but the exponent itself is the variable, as you can see here. So these are examples of exponential functions, where the base, as we see here, is 10, is a positive constant. And we'll look at some of these as we go on. Now, when we look at exponential graphing, we say, of course, it's not linear, it's not a straight line, and this type of graph shows exponential growth. So we want to look at this. F of x equals 2 to the x power, and remember we said we can always substitute a y here. So y equals 2 to the x power. What we could do is we can take some points for x and then solve it and see what we get for y. Now, I'm repeating what they've done here, but I'll work it out for you. And I'm going to start here. These are the easy ones. So 2 to the third power is 8. 2 to the second power is 4. 2 to the first power is 2. 2 to the 0 power, anything to the 0 power is 1. It's a funny looking one. There we go. Now, as we go to negative exponents here, 2 to the negative 1 is equal to 1 over 2 to the first. So in a sense, the reciprocal of this, which is 2 to the first is 2, so the reciprocal of 2 is 1/2. And then negative 2 would be 2 to the negative 2, which would be 1 over 2 to the second, which is 1/4. The reciprocal of 2 to the second power, which is 4. So this will be 1/4. And then 2 to the third power is 8. So 2 to the negative 3 is 1/8. Okay, I just thought I'd show you how you do that. And now you start to plot them. So we can do it this way. Negative 3, 1/8 is sort of close. 1/4, you go up just a little bit there. Negative 1 is 1/2. 0 is 1. And then now these are easy. These go at 2. And this is at 4. And this is at 8. So you get this nice curve. So this is one you want to have in your notes, and you want to know how we got it. Well done here. This shows what we said before, exponential growth. Now they're actually asking if this were f of x equals 2 to the 50th power. How high up would that go? Well, as we see here, 2 to the 50th gives you this enormous number. And then we want to convert it to miles here. So we divide it by these things, and it would be over 2 billion miles. Wow. So that is really an example of exponential growth. Okay, and of course here our value is greater than 1. Now, suppose we did this with y equals 3 to the x power. What would these be? Let's fill these in here. We'll start here. This will be 27. 3 to the second is 9. This would be 3. This would be 1. Remember, anything to the 0 power is 1. And then now we get reciprocals. This is 1/3, 1/9, and 1/27. So if we were to plot that, and then I like the way they're showing this, here's the one we already did, and then this one would be this one now, what we plotted here. And if we had 10 to the x power, what seems to be happening as the numbers get big? We had 2 to the x, 3 to the x, 10 to the x. These were exponential equations that we were setting up. When we made a graph of them, this was our 2 to the x. You see what happens when we went to 3 to the x. It went a little closer to the y-axis. And then 10 to the x, a lot closer. And then 11, 12 would all be closer. Well, how about if we had, instead of a 2, we had 1.5, which is 3/2 to the x power. Well, instead of going closer, it would actually go a little further away. So again, this is something that, sketch it in your notes. I should have that in your booklet. And then you want to develop a little understanding for what's going on here. So in summary then, the graph is above the x-axis. The y-intercept is always a 1 right there. The graph climbs steeply to the right. And we didn't mention this, and I certainly want to, that the x-axis is actually your horizontal asymptote that we talked about last section. That this gets closer and closer to 0, but never reaches it. Remember, the equation of the x-axis is y equals 0. Now, the larger the base, if it were 2 to the x, 3 to the x, it gets more steep. That is, gets closer to the y-axis. And if it's a fraction, less than 2, it gets a little spread out this way. Now, we haven't gotten fractions less than 1 yet. That's coming up. As we see in example 2, consider this function. Well, again, to put this in a positive exponent, it becomes 1 over 2. This goes down to the denominator, and our sign of the exponent changes, which then can be interpreted this way, and that's what they're showing here. So what would happen here? Well, again, let's make a graph. So setting up a t-chart, which is what they have here, if we have 1/2 to the -3 power, we said that we could, when it's a negative exponent, flip this And this would be then 2 over 1, taking the reciprocal of this, and that makes that a 3. So we're going to take the reciprocal of 1/2, which is 2 then, and raise it to the positive 3 power, which is 8. So then this is going to be 4. This will be 2. Anything to the 0 power is 1. But now in this case, it's the reciprocal, 1/2, 1/4, 1/8. And you can do the math if you want, but there it is laid out. So as we see it here, we see the basic shape is similar, showing exponential form. But what we had on the other, you may recall, and I'll change colors to show you, this was a 1, this was a 2, this was a 4, and this was an 8. So if we make this curve, and it went down like so, we now have what is called an axis of symmetry, where on either side, this was y equals 2 to the x power. This one will be y equals 2 to the negative x power, which we said was y equals 1/2 to the x power. And there we see that one is sort of the mirror image of the other. I didn't do a very good diagram here. But we see there's the 1/2, there's the 1/3, there's the 1/10. And once again, to just show you the symmetry of this, the 10 was over here, the 3 was over here, the 2 was over there, and the 3/2 was over there. So as the fractions now get smaller, they get closer to the y-axis, which we are describing as, when we have all of them there, our axis of symmetry. So once again, if it's a fraction less than 1 but greater than 0, it will appear as a graph from this side. And again, your axis, your x-axis, is your horizontal asymptote, as they say here. Okay, and as it got a smaller fraction, it would get closer to the y-axis. Now, example 3, we've done this pretty much. They want us to put both of these on the same graph. So this is showing what is called the mirror or reflected image, one side to the other, with the y-axis being your axis of symmetry. Now, as we look at letter B, we have 3 to the first power, which will be a 3, minus x. So as we put this negative exponent in there, this will be a fraction, and we're going to compare it to just this without the 1. So you need to remember this a little. We'll see that in the next picture, what happens. Well, we already know what this is going to be. This is going to be like 3 to the, or the 1/3 power raised to the x, which moves it this way. It goes through 1, and then these are values that go there. But now when we have 3 to the 1st, our point of intersection is going to be 3. So you see it shifted it up. But basically then it's a similar curve. It's shifted this up. It's still gone to the right. And our horizontal asymptote is still the x-axis, which is y equals 0. And then for letter C, we're comparing these. Now we know this one already. That's the one in red. But when we are taking a fraction of 1 as 0.6 and using that, it makes it less close to the y-axis. That is, it spreads it out and drops it down to something like this. Okay, so I have both of these in your booklet, and you want to have some notes as to the meaning of it. Now, looking at example 4, if we have a graphing calculator, this works so much better. Otherwise, you have to develop a chart and then get some points. Now, you're going to use positive and negative, and your graph ends up looking like this. Notice that when x is 0, anything to the 0 power is going to be 1. So it looks like so. And that is the basic shape of this type of graph. Now I have a graphing calculator, so I was able to actually put this in there, and this is the graph I got. So again, it's still going through 1 and looks something like that. Now at this time in our textbook, they're introducing the number e, which is a useful number. It's in our calculator. It's an irrational number, and it plays an important role in compounding of interest. It's also in various other scientific and mathematical contexts. 2 12 decimal places, and since it's irrational, continues, so we give approximation, but we can often round it off to 2 decimal places as 2.72. Now if we have e to some exponent, our base would be this. And let's take a look at what this would look like. So to do a little of this, e to the x power, if it's -1, that would be 1 over 2.72. And then e to the 0 power, as any number is to the 0 power, is just going to be 1. But now e, which is 2.72 to the first power, is just 2.72. And then we square this, and it gives you, something close to 8, but not quite. So let's check it out here. So we get some values down here. It's going to go through 1, and then now it's going to go over 1 right there at 2.78, right about there. So we see that's where e is, this blue line. And then as we go up to 2, it goes up there, around 8-ish. Okay, so you get an idea that it too can be plotted, and we can have an exponential power expression of e. In example 5, we're going to look at how this applies to business, some applications, the amount of wine in millions of gallons consumed in the U.S. can be approximated by this function, where they are using e, and it's to this exponent as a decimal times x. Now, 0, when x is 0, that corresponds to the year 1950. So how much wine is consumed in the year 1970? Well, that's 20 years from then. So we get 20, where we put 20 and replace it with the x. We multiply this. We then get a value. That's our exponent. We then put 139.6 times e in our calculator. Then hit the caret button and put this in as your answer, which is the product of 0.31 times 20. And you could do that ahead of time if you want and have a value for that. And it gives you approximately this many millions of gallons. Ooh. How about in the year 2010? Well, we go from 1950 to 2010, that's 60 years. So again, you might want to multiply 0.30 times 60, get a value. Then you're going to go 139.6 times e in your calculator, caret, and then put this product in there, and you see it's this. Now, use a graphing calculator to determine when the consumption would reach 1,000 million gallons. Wow, that's a lot of wine. So how do we do that? Well, one way to do it is to put this into your graphing calculator and then put a second line equation in as y equals 1,000, which is this line up here, and then use your tracing tool, and it gives you y is about 1,000, and this would be 63.5, so about, adding that to 1950, so about 2013. Okay. Again, depending on what we're going to be doing as your assignment as to what you would have in your study plan, how we're going to include a calculator that you can use to figure this out. We're not using a graphing calculator, so at this time we wouldn't expect you to be able to do this. Actually, we're building up to where you could be able to do it toward the end of the course. Now, for example 6, it says when a patient is given a 300 milligram dose of the drug cimetidine intravenously, the amount of the drug in the bloodstream after T hours is given by this function, where T hours. So again, we're putting this into our calculator, and the T is 3. We'll get this. After 10 hours, it would be this. Now, the doctor wants to give a patient a second 300 milligram dose when the level of her bloodstream decreases to this. So how long would that be? Well, again, you're going to use two equations like we did before. You put this one into your graphing calculator, and then y is 75, and using your tracing tool, it comes out to be approximately 4 hours later after the first dose. This is a 4. 1, 2, 3, 4. Again, it would be nice if everyone were required to use a graphing calculator, and that would be so much easier because the book features that somewhat. But again, I don't think we are requiring you to do that. And here we see a few exercises in our textbook. Let's take a look at them. Classify each function as linear, quadratic, or exponential. Well, here the exponent is our variable, so this is exponential. This is to the second power, so this is quadratic. Here our variable is the exponent, exponential. Our variable is to the first power, so that's linear. This is exponential, and this is exponential. All right, here they're asking you to describe the shape of the graph of each function. And then again, using your notes, you ought to be able to do these, and then give a general graph shape of these. Again, if you had your graphing calculator, it would work out really super. All right, we'll wind this up.